Hello, everyone. I'm Abhinav, one of the founding engineers at Activeloop, and I'm excited to present to you today Deep Lake, which is a lakehouse optimized for deep learning applications. So before we get into the details of what Deep Lake is, let's take a step back and look at the deep learning ecosystem from the past few years. We've seen the growth of large and foundational language models, and with models now reaching even 1 trillion parameter size. So these models contain a lot of information, and some people have even started comparing these with databases. If someone has used ChatGPT here, you might even agree. So these models are trained all kinds of data, including text, images, audio, and video. In fact, recently, one of the things that these new models have unlocked is the possibility for us to generate images just using simple text descriptions. You might have seen examples of this floating around on social media with outputs coming from Stable Diffusion and DALL-E, which are really high quality and are just based out of text descriptions. So these all models are huge, but another important aspect for them is the underlying data on which they're trained, which is in many cases even more important than the model architecture itself. However, working with large amounts of unstructured data, such as audio, video, and images, is hard. In fact, 1 out of every 3 machine learning projects fails due to poor data development practices. So traditionally, data lakes have been used to solve this problem. They allow organizations to store all their data in a central location and integrate it with their data stack. Data lakes have a lot of benefits. So the data is present in a central location, so the entire organization can easily access it. So this breaks down the data silos and enables data-driven decision-making as everyone has access to the data. And apart from this, they also improve operational efficiency and reduce costs compared to storing data in a traditional database. Moreover, there was a second generation of data lakes, which included Delta, Hudi, and Iceberg, which not only had these functionalities, but also had functionalities including time travel, parallel ingestion, and connections with query engines. Apart from that, there was another wave of lakehouses which came in, which essentially integrated the second generation data lakes with query engines and made those compete with databases and data warehouses for analytical, historical, and predictive queries. However, for complex data processing, including images, videos, and audio, there are still a lot of limitations. It's not supported properly. There are missing deep learning integrations. There's a gap between MLOps and the modern data stack. Moreover, the SQL queries are typically for traditional use cases, such as analyzing the sales of a company for a given quarter, and don't necessarily translate into deep learning applications. So this is where Deep Lake comes in. It is a lakehouse designed to address all of those issues and make it very easy to work with unstructured data. It consists of the following 5 features that enable us to do so, starting with the tensor data format, the large-scale version control, ML-focused queries, in-browser visualization of large-scale data, and data streaming. Let's take a deeper look into all of these one by one. So it all starts with the tensor data format. So it's the storage format. As we discussed in the previous talk as well, tensors in deep learning are containers of numerical data that reside either on the CPU or on the GPU. Deep Lake uses the same concept, but extends it to bigger data sets, which will actually reside in local or cloud storage, while keeping the data as accessible as regular tensors. The different types of data are stored as separate tensors to allow fast access of individual columns. And these tensors are chunked at the time of upload. And this is useful for working with smaller data, as a few large requests can be made instead of many small ones. And this improves the throughput while accessing data from a cloud source. So this unstructured data that we support can vary a lot in size and shape. So we use a dynamic chunking strategy instead of a static one, and the details of that are detailed in the paper itself. So the format natively supports a wide variety of data, including tabular, video, images, text, medical data, and links. Links are essentially a way to store pointers to the original data and use deep lake without duplicating any of the original data that you might have. So another key aspect of deep lake is version control of large scale data. So as I mentioned before, existing second generation data lakes provide time travel based version control, which doesn't really fit in with the traditional ML cycle. Because usually there are multiple users who are working on the data. They're making some changes or pre-processing it. So just going back in time doesn't necessarily give you the full view of what happened and what steps were taken and by whom. Deep Lake lets you track the evolution of data at each step, starting from the raw data to its processing, all the way to the final view of the data set that's sent for training. It provides the ability to use Git-like version control of data through the Python API itself, instead of the traditional CLI implementations. We went for this approach because we've seen that most deep learning applications actually process the data using Python scripts themselves. And we wanted to integrate the version control tightly within those scripts instead of having the programmers switch back and forth between the CLI and their scripts. So here is a simple example of a workflow that works with Deep Lake. You just start with an empty data set, add a bunch of images to it, simply check out to another branch. Maybe someone else is working on it. They append a lot of annotations. Once they're done, they can merge it to the main branch and they can continue work from there on. So this is very similar to a Git workflow. So often during ML cycles, subsets of data sets containing certain characteristics are required. This could be for training, fine-tuning, or simply just inspecting the data. Deep Lake has the ability to query data sets and construct views based on various conditions. So in some cases, these conditions might be really simple and they can be expressed using SQL. But we also have introduced an extension of SQL called Tensor Query Language, or TQL, which can be used for more complex scenarios. It extends SQL by adding the possibility to support expressions on multi-dimensional arrays. It supports Python-style indexing, and it also has predefined functions to work with arrays. This allows users to express complex conditions directly in the query language. So one example of this could be if you're training a self-driving car and you've trained it on billions of samples. However, there's an unlikely edge case that you might have missed out on. People don't usually ride cycles in the rain. I think we are in Amsterdam, so it might be different here. I've seen people driving around, but in the general case, that's usually not what happens. So it could be that the model is not trained enough on such a scenario and it might malfunction. So in order to counter that scenario, you can identify that edge case and run a query to just isolate the samples that satisfy that particular condition. This is one such query that can be run on a data set. And this will get you a subset, a few examples on the right side of that. And that subset, we're also slicing the data. If you can see here, we're slicing the images, we're adjusting the bounding boxes within the query itself, and we're ordering the output that we're getting. So once we get this output, we can actually augment it and use it to fine tune the model that we have in order to make it perform better on this particular edge case. These queries are all quite powerful and can also be used for sampling and in order to fix the data set that has a very skewed distribution in which certain classes might appear much more often than the others. So sampling as a part of the query can also help with that. So another integral part of the ML cycle is inspecting and analyzing the underlying data. Deep Lake allows streaming data directly from the storage to local devices where it can be viewed on the in-browser visualizer. And this data comes directly from the storage to the browser without it going through any middle party or through us. So this visualizer allows users to inspect the data both quantitatively and qualitatively. One can inspect the actual data, which could have millions and hundreds of millions of rows, look at its distributions, and even run queries in real time and see how the data set changes when you run a query. So the last key feature is the streaming data loader. So this data loader plugs directly into both PyTorch and TensorFlow and allows fast streaming of data from cloud storage directly to the model as if the data was present locally. Here are some benchmarks comparing the performance of Deep Lake to some of the other mainstream data loaders. So the first one compares the iteration speed compared to some mainstream ones like FFCV, Squirrel, PyTorch. And the next one compares training ImageNet in 3 scenarios. The first scenario involves copying the data from S3 to the local storage and then running the training. The second one uses AWS fast file mode, which is optimized for streaming. And the third one uses Deep Lake streaming. So less time taken here for training is better here. So fast data loaders are becoming more and more important as data sets get bigger. With training jobs taking weeks and even months and running on expensive multi-node clusters, even small improvements in the performance can add up to big savings in price and also time. So the performance of the data loader can be attributed to 2 main reasons. One is that we have a smart data-aware scheduler, which prioritizes CPU-intensive jobs. And the next is that we do prefetching using C++ threads instead of Python threads, which many of the other implementations use because of the infamous global interpreter lock, which slows down many Python implementations of data loaders. So finally, here's an example of a real world use case. This is the Lion 400 million data set, which contains 400 million text image pairs. And it has a lot of samples. And this is one of the biggest openly available multimodal data sets. So the data set, if you try to retrieve it, is present in the form of 50 GB Parquet files. And those Parquet files contain a lot of links to the actual underlying images. So if you try to do it in a normal way and convert it into web dataset format, retrieving the data and converting all of this, it will take you 100+ hours easily. The final data set size after you've retrieved is 20+ terabytes. On the same machine, we were able to do this in under 6 hours using our parallel ingestion. And then once we have the data set stored in our format, it's pretty trivial to use it in a single line of code, run a query the next line, and then send that queried view of the data set to a data loader, to PyTorch or TensorFlow, wherever you want. And this is actually replacing hundreds of lines of code, which you would otherwise have to write if just starting from scratch or even using alternate libraries. So here is how Deep Lake plugs into the entire machine learning loop with the labeled data coming in, all the steps, including version control, visualizing data, querying it, transforming it, and streaming it back to the machine learning frameworks, and thus completing the entire cycle. And so I'd like to conclude by saying that TensorFlow, PyTorch, and other libraries in Python have solved the compute problem. And now it's time to unlock the compute from the data bottleneck. And that's what we're trying to do at Activeloop with Deep Lake. Yeah, so it's an open source format. You guys can check it out on GitHub. And I'm happy to hear any questions. And although it's me, Levon, and Sasun, we're here from Activeloop, so feel free to even ask us after this. And yeah, any questions?
Excellent.